Hello everyone. So welcome to this exciting lecture on the course for optimization of water distribution network. So till now we have seen why do we need optimization and then how can we optimize a system using the fitness function, which is our total cost plus the penalty for any constraint failure. Then we also saw the various methods by which we can optimize a water distribution network. Now we need to learn how the computer searches for the minimum cost, and we begin with the simplest search structure, which is the linear programming. So as you can see that various research papers have been published based on optimization on the lines of linear programming. Linear programming is one of the oldest and simplest form of optimization. It has three strict and non-negotiable rules. So if you violate these rules, the solver will fail. The first rule is that the objective function must be linear, right? And then the rule number 2 is that all the constraints must also be linear, right? Then the simple straight line we can say. And the rule number 3 is that all the decision variables must be continuous. It should not be discrete whole numbers. And this is where the water distribution networks fail, because they are in discrete steps, the pipe sizes especially, and everything in water distribution is not a linear function. For example, you see Hazen-Williams, so things have a coefficient which are non-linear in nature. But in this method we are just trying to understand the structure of optimization, right? So we will try to linearize everything. We will try to put a linear relationship, that is y is equals to mx plus c, where m and c are constants and x is dependent on y, right? So here in linear programming we will be looking for the minimum or the maximum objective function, and when we build a function, then we will have two variables which can be plotted, and then within the constraints that are there on a piece of graph, and the area where all the constraints are satisfied will be our feasible region, right? So every point inside this area will be a valid solution, and the linear programming guarantees that the best solution always is found at one of the corners or the vertices of this feasible region. Now the question is whether you understood this linear programming or not, and the second question is how can we apply this to a water distribution network, right? So even if you have not understood a single word what I said in this video, now you will understand everything when we move on to the hands-on. So what we have to do here is we have to linearize the reality, which means simplifying the system drastically. So here we must pretend that the cost of the pipe area is linear, and most importantly we must ignore the true non-linear head equations like the Hazen-Williams, and this simplification is only for learning the linear programming structure, right? So now we start with the example, and then we will try to build this example in an Excel environment. So you will learn linear programming from basics to complete Excel solver method. So this is the problem for today. So imagine that you have three parallel pipes P1, P2, P3. And you need to determine the flow split through them to meet a total demand of 100 liters per second. And your goal is to minimize the pumping cost, where the unit cost of moving the flow through each pipe is a fixed cost. And the head loss through each pipe is H1, H2, H3. And the cost function C1, C2, C3. And accordingly, the discharges will be Q1, Q2, Q3. Kindly read the discharge in the pipe 2 as Q2 and pipe 3 as Q3, right? So now this is the problem set. Now what we will do is we will try to define this problem in an Excel environment, and then we will try to find a solution, the optimized solution, and see how linear programming is done automatically by Excel. So you will learn a very new thing today. Now the important thing here is when I am going to teach you in this Excel, the good part is I will be giving you the link for this Excel in the description below. So let's move on to the Excel environment. You can download this sheet from the description below, and then we see what is there in this sheet. So the first row says input and constant data. So here we have to put the total demand required, which is 100 liter per second. So we put that. Then the maximum allowable head loss. So the maximum head loss that is allowable during the course of transmission of water from one end to the other. So let it be 5 meters of head, and then we can input some cost factor for each of the pipe. Okay, this has been done to linearize things on a linear basis, that what is the cost of each pipe. So a linear function for all the different kind of pipe has been given. So let it be 0.5, 0.8 and 0.65. And then there are 3 pipes, pipe 1, 2, 3, in which we do not know the flows yet. And here will be the cost, that will be the cost factor into the corresponding flow, and here it will be a head loss. Now instead of using a non-linear relationship between head loss, I have just given it as 0.001 into the flow, that is a linear constant into a variable, a constant into a variable. So here the friction factor has been taken as 0.001, here it is 0.002, and in this 0.0015, just to make things in a linear format, right? To see how things work in a linear fashion. And once you learn things in one dimension, then slowly we can increase it to many dimensions, right? And this is the total cost that has to be minimized, which is our objective. And here it is the total sum of flow, and this is the total sum of head loss, right? Now we click on the data tab on the top ribbon, and then we go to solver. If you don't find this tab, you can Google and see how to bring this tab using the developer option. Then we are here in this solver option, and then we first set our objective, that what is it that we need to do. So here we need to minimize our cost. So which is the column number, and row intersection is F6. So this is what we need to do, and what we need to do with F6, we need to minimize it. So we will select minimize, and then which variables we have to change to minimize it. So we have to change the flows, right? These 3. So we will click here and then we will select these three, and then we will hit enter. So E2 to E4, right? Then now we have to add various constraints. So the first constraint will be that the total flow must be equal to 100, right? So how do we put that constraint? So we will click on add, and when you click on add, these things come, and then we want to make the total flow, that is this one, equals to, so we will select equals to this one, 100. Okay, so one constraint has been added. Then the second constraint is the maximum allowable head loss. This one must be less than or equal to 5. So F9 is less than or equal to 5. Okay. And then last constraint that we need to add is that flow in any of the pipe cannot be negative. So we select these three, and then must be equal to or greater than or equal to 0, right? So these three are our constraints. So we have set the environment, and then make sure you check that the unconstrained variable are non-negative, right? And then from here we select the linear programming method, right? So it is saying that the solver has found a solution and all the constraints and optimally conditions are satisfied. So we have found the optimized solution, and that is, it says that the pipe 1 should have all the flow and the other pipe should not have any flow. So this is the optimized condition as per this particular constraint situation. Now you can always play with these kind of things and situations, right? So this was just to give you a demonstration of how things work on a smaller scale when very few number of pipes are involved, and obviously we are going to see when and what happens when a larger network is involved. If you have liked this video, consider supporting us by the thanks option or by joining our channel. Thanks for your valuable time.